Hello everyone, thank you for watching this video. My name is Peiyao. I'm a graduate student from UIUC. This talk is about ACeD, a scalable data availability oracle for blockchains. Before I start, I'd like to thank my collaborators, Bowen and Professor Sreeram Kannan from UW, and my supervisor, Professor Pramod Viswanath from UIUC. Today's talk mainly contains two parts. The first part discusses our motivation. We want to take out the trust from trusted blockchains and build applications with it. But this idea is acknowledged to be vulnerable to the data availability attack. To solve this problem, we set up a model called Data Availability Oracle and proposes a scalable solution, ACeD. We will compare ACeD with other solutions to show our advantage. The second part presents technical description of ACeD, including its model and design, what security and performance it guarantees. At the end, we will demonstrate our implementation and show the evaluation result. Public blockchains such as Bitcoin and Ethereum have demonstrated themselves to be safe and live in practice for a long time, but their performance is not satisfactory. To improve the performance, a major research area in recent years focuses on designing new blockchain protocols with high performance without sacrificing security, like Ouroboros and Prism. These solutions always entail a wholesale change to the core blockchain stack, which makes the upgrade of existing blockchains full of practice hurdles. Then, to address this concern, high-throughput scaling solutions are explored via Layer 2 methods, including payment channel and state channels. These solutions use existing blockchains as Layer 1 structure, but also their computations are closely tied to the original blockchain and involve locking the main chain state, which limits the application scope. Our work starts from a different mechanism to scale the blockchain performance, where some smaller blockchains derive trust from larger blockchains by committing the hashes of these blocks periodically to the trusted blockchain. It still stands on the same Layer 1 structure, but with more flexibility and further provides a much simpler, more efficient, and practical way to support different applications. The figure depicts the mechanism of side blockchains. By committing hashes, the order of blocks in the side blockchain is determined by the order of hashes in the trusted blockchain. This way, the security of side blockchains is directly derived from that of trust blockchains. However, this simple mechanism faces a serious vulnerability called data availability attack. An adversary node can commit the hash of the block without transmitting the block to any other nodes, which violates the liveness of the side blockchains. To solve this problem, we propose an intermediate oracle layer that interfaces between the side blockchains and the trusted blockchain. The oracle layer accepts blocks from side blockchains, pushes verifiable commitments to the trusted blockchain, and ensures data availability to the side blockchains. The oracle nodes inside the oracle layer will work together to reach a consensus about whether the proposed block is retrievable or not. There are several straightforward constructions of the oracle layer. We can let every oracle node store a full copy of data, which is apparently secure but not efficient. A more efficient way is to disperse the block so that each node only needs to store part of the block. However, this way, only one malicious node can violate the retrievability. So it appears that there is a trade-off between security and efficiency. And the key challenge is how to design an oracle with both of them. The starting point of our solution is the utilization of erasure coding. With NK Reed-Solomon code, K data symbols can be used to generate N-K parity symbols. So there will be N coded symbols in total. These coded symbols are further dispersed among the oracle layer. Given the undecoded ratio alpha, the network can tolerate the bilenting parties, hiding up to alpha-coded chunks. And the use of ratio codes improves the security. At the same time, it brings two key issues. That is how to ensure the integrity and the correctness of coded symbols. Intuitively, we can use a Merkle tree to provide the integrity proof, as is shown in this example. But a malicious block producer can construct a Merkle tree with a bunch of rubbish symbols to launch incorrect coding attack. In this way, even if we have access to enough coded symbols, no one can reconstruct the block from them. To detect such attacks, there are some existing solutions. The paper Asynchronous Verifiable Information Dispersal uses a method where nodes broadcast received data and meanwhile download others' forwarded data to check whether they can reconstruct the original block. It's easy to notice that the communication efficiency is sacrificed here, since all nodes need to download all data chunks. An alternative approach is to use an incorrect coding approve. A client who wants to retrieve the block will request chunks from Oracle nodes. When the attack happens, the client will find the block undecodable, even with enough data, thus can detect the attack and generate a proof to notify Oracle nodes. In this way, Oracle nodes just need to download a proof to check the coding correctness. In terms of the proof, we found that simply applying one-dimensional Reed-Solomon code, the size of the proof is essentially not much smaller than the original block. For reducing the size of the proof, Mustafa and coworkers proposes to use two-dimensional Reed-Solomon codes, with which the proof size reduces to square root of b log b. Furthermore, a recent work by Minchao and coworkers proposes a new hash cumulator named coded Merkle tree, and further reduce the proof size to log b. This provides us a near optimal proof size. CMT already provides us an efficient way to detect incorrect coding attack. It uses a random sampling-based method to help light nodes check the availability of blocks. However, remember our target is to construct a data availability oracle. Only with this mechanism, rational oracle nodes are naturally incentivized to mimic others' decisions without storing their own data, which is also known as the information cascade problem. In other words, when oracle nodes claim they have received enough data, there's no way for clients to check the correctness of their statements. So CMT itself fails to solve the oracle problem. Then, inspired by the efficiency of CMT, we proposed a new protocol called Authenticated Coded Dispersal. Instead of random sampling, we designed a deterministic dispersal protocol to ensure the reconstruction of block without sacrificing the efficiency. Further, it is also designed to be incentive compatible, thus eliminate the problem of information cascade. Generally, our protocol consists of 4 components: a commitment generator, a dispersal and retrieval protocol, and a block decoder. The details of the system will be discussed later. Before moving on to the technical part of our protocol, I'd like to show the performance comparison among all the solutions we've mentioned so far. The comparison is conducted by these 4 metrics. First, beta is the maximum fraction of adversaries the protocol can tolerate. The range is from 0 to 1/2. Second, storage overhead is the ratio of total used storage and total information stored. The range is from O1 to OM, where n is the number of oracle nodes. Third, download overhead is the ratio of downloaded data sets and the size of reconstructed data. The range is also from O1 to OM. Last, the communication complexity is the total number of bits that have been communicated. The range is from OB to OMB, where B is the block size. As we can see in the table, the weaknesses of all the other solutions we've analyzed are consistent with the calculation. For instance, the repetition protocol has large storage overhead as well as communication complexity. The uncoded dispersal cannot tolerate any fault. And the communication complexity of ACeD is no better than the simple repetition. And the storage and download overhead in the worst case for 1D to DRS are still large. In comparison, ACeD achieves optimal storage, download, and communication overhead under the normal path, and the near optimal storage and download overhead when the block producer is adversary. So far, we've introduced the motivation and the problem of data availability oracle and shown the advantage of our solution. Next, we will formally present and analyze our protocol design. First of all, we specify our system and security model as follows. The system is made up of 3 components: a trusted blockchain that stores commitment and decides ordering, an intermediate Oracle layer with Oracle nodes that ensures data availability, and clients, those are the nodes inside blockchains who propose data. The key assumption of our system is that the trusted blockchain is safe and live. That is, it has a persistent order of data and aliveness for its service. Besides, we assume that in the Oracle layer, there is a majority of honest nodes. For clients, we only assume that at least one client is honest for liveness, and they can connect to all Oracle nodes. Then the network is synchronous, and the communication is authenticated and reliable. The pipeline of ACeD protocol is depicted in the figure. The first building block is a coded commitment generator, which takes a block proposed by a client as an input and creates 3 outputs: a commitment, a sequence of coded symbols, and their proof of membership. The commitment generator we use is a tree-based hash cumulator called the CIT. The root of CIT is the commitment we output. The leaves of CIT in the base layer are the coded symbols. And the proof of membership of a symbol includes those circled intermediate layer symbols. Among them, the solid circle symbols are the Merkle proof, just like in a normal Merkle tree. And the dashed circle symbols are a set of parity symbols from different layers. Now let's go through an example to show the construction process of a CIT. In this example, a block is divided into 8 data chunks, and further used to generate 24 parity symbols, so there are 32 coded symbols in total in the base layer. Then by aggregating the hashes of 8 coded symbols, we get a data symbol for its parent layer. There are 4 in total. The aggregating rule is that the parent ID is equals to the children's ID mod the total number of data symbols in parent layer. So as we can see, those symbols who have the same parent are congruent when module 4. Then applying the same erasure code again, we get 16 coded symbols in the second last layer. Similarly, we get 2 symbols for its parent layer, and they are encoded into 8 coded symbols. Then the next layer, 1 data symbol, 4 coded symbols, and finally, we got the root of the tree. Then let's see how we generate the proof of membership given a base layer symbol. When the base layer symbol I is dispersed, for each intermediate layer, 2 symbols will be included in POM. Specifically, they are the PI's data symbol and EI's parity symbol, where PI is I mod the number of data symbols in that layer, and EI is I mod the number of parity symbols in that layer. For example, when a node receives the symbol number 15, its POM will automatically include all its parent and parent of parent, because the construction rule makes the parent ID equals to I mod the number of current layer data symbols. Besides, it will include some parity symbols following the rule. So 15 mod 12 is 3, the 0, 1, 2, 3, and 15 mod 6 is also 3. 15 mod 3 is 0, so this one will be included. Given the construction rules of CIT and POM, next we're going to see how they help the system to be efficient and secure. The first property of CIT says that for any intermediate layer, PI and EI are siblings. According to the aggregating rules, it can be observed that in each layer, the data symbol and parity symbol associated with the same base layer symbol are congruent module the number of parent data symbols, thus they're siblings. And we already know that the data symbols in POM constitute the Merkle proof of themselves. So this property further ensures that no extra Merkle proof is needed for those parity symbols in POM, thus ensures the space efficiency. The second property of CIT ensures reconstruction. It is said that if there is a subset of base layer symbols which are more than some fraction eta, then the POM of those base layer symbols must contain more than eta fraction of symbols as well for all the intermediate layers. This property ensures that if a subset of base layer symbols are enough to reconstruct all data, then the entire tree can be reconstructed. With the help of CIT, we've got some coded symbols and their POM, which will be dispersed among the oracle layer. So a dispersal protocol is needed to decide which oracle node needs to store which chunks. A dispersal protocol encapsulates the following process. Consider there are n chunks to be dispersed to n oracle nodes, and each node receives k coded symbols, such that any gamma fraction of nodes together contains eta fraction of chunks. With such a dispersal protocol, we let eta greater than 1 minus alpha. Remember, alpha is the undecodable ratio. So the commitment, along with gamma plus the adversary fraction beta, those votes can be submitted to the trusted blockchain to ensure the data availability. Once the commitment of a block is submitted to the trusted blockchain, afterwards, when a client wants to retrieve the stored block, the retrieval protocol will ask the oracle layer for data chunks. Our dispersal protocol ensures that at least eta m symbols with their proof of membership are retrievable since they are held by honest. And further, remember that CIT provides us the reconstruction property, so that the retrievability of base layer symbols indicates the retrievability of the entire tree. With these properties, we can use a hash-aware peeling decoder to reconstruct the block. The construction process is from top to down. The hashes carried by the recovered parent layer will be used to verify the correctness of the next layer. When a failed equation is detected, the symbols in the equation, as well as their Merkle proofs, form the incorrect coding proof and will be stored in the trusted blockchain to permanently recode the invalid block. We also implement our protocol with full functionality in real world to evaluate the performance. The system we implemented also consists of 3 components: the trusted blockchain, the oracle node, and the side blockchain node. In experiment, we use Bowen and Ethereum testnet as our trusted blockchain. The design of side blockchain node contains 4 modules, a block database, and a mempool. And the design of oracle nodes contains 3 modules and a symbol database. Each side blockchain node owns 2 network interfaces. It communicates to the trusted blockchain for pulling the latest state digest, and it talks to oracle nodes for reassembling the block or publishing its own block. A smart contract manager is used to pull states on the contract regularly, which includes the block height and hash digest. When states change, the contract manager talks to a trusted chain manager to keep the local chain consistent to the global states. And if some blocks are not available, the chain manager will talk to the block manager to acquire new blocks from oracle nodes. A scheduler here tells a sidechain node when it can propose a block, and experiments we did by time into slots and have a deterministic mapping from slots to the node in a round-robin manner. Once a node finds its turn, the scheduler will ask the block manager to encode the mempool with LDPC code. Every oracle nodes also have 2 responsibilities. The first is to store and offer block symbol on request from sidechain nodes. The second is to vote honestly for committing any proposed block to the main chain. If a side blockchain node proposes a block, the oracle node will check with local scheduler. If a proposal block passes all checks, including its symbol validity check and time requirement, an oracle node will accept the symbols and broadcast its votes to other oracle nodes. A smart contract manager here is responsible to talk to the trusted blockchain if the node has collected a sufficient signature for the block. On top of the basic system, we have also implemented some optimization techniques for better performance. The first is for LDPC code. LDPC code has high encoding complexity. We use multi-threads to speed up the procedure. On the left side is an inverse coding map. The key of the map is the input index, and the values is a list of parity symbol indices that need to XOR the inputs to get output. On the right side is a single producer multiple workers architecture to parallelize the encoding process. Workers partition the space of parity index so that encoding can happen simultaneously on both workers. Notice that the input symbol with index 1 is only needed by parity symbol 5, so symbol 1 does not have to be sent to worker 1. In addition, since XOR is both commutative and associative, the order which a worker receives those symbols does not matter. Experiment shows that 4 threads can save 1/3 time of work of a single thread. A simple running schedule generates a new block only if the previous blocks are committed and reassembled at each local node. This approach couples the throughput with processing latency. And the goal of pipeline is to allow multiple blocks being processed at the same time. We allocate multiple threads to side blockchain nodes and the Oracle nodes, such that the block processing at all modules has its own processing thread, which won't be blocked by any previous block. And if a block is committed to a trusted blockchain before its previous unfinished block, the unfinished block is automatically invalidated. In this way, we decouple the throughput and latency completely. We test the system performance with different number of side blockchain nodes, Oracle nodes, different block size, and block generation rate. In the first 2 experiments, we see the number of Oracle nodes and side blockchain nodes does not have noticeable impact on throughput and latency. In the third experiment, we increase the block size and observe a more significant change in latency and throughput. The latency increases because larger blocks require more onerous encoding, but the throughput is also linearly proportional to block size. In the last experiment, we fixed the product of block generation rate and the number of sidechain nodes to be constant. As blocks are generated more frequently, the throughput almost increases linearly. And our overall throughput reaches up to 10,000 transactions per second and 6,000 times reduction in the gas cost. At the end, I'd like to give a summary of this talk. The main idea behind ACeD is to transfer the trust from trusted blockchains to side blockchains. And to solve the possible problems, we develop an abstraction of data availability oracle. Among multiple constructions of the oracle, we demonstrate that ACeD achieves near optimal performance on all the metrics. And we also go through the model, the specification, and the implementation of ACeD to see how it is both secure and efficient theoretically and practically. However, when instantiating the system with specific parameters, we've seen the bottleneck of ACeD is that undecoupled ratio is lower than other erasure coding-based methods. Therefore, finding a deterministic LDPC code with a higher undecoupled ratio will immediately benefit the practical performance of ACeD. And the construction of such codes is also an exciting direction of future work. That's the end of my talk. Thanks for watching.